is on a related but quite richly diverse and different topic from the first two lectures. So I'm going to talk mostly about, or only about, non-convex optimization today. And the way I'm going to talk about it, given the vast diversity of the subject, I decided to rather give you a pseudo overview of several different existing ideas in the non-convex world with some concrete examples. And the reason for that is some of these ideas that I'll tell you, this don't seem to be that well known, but they're quite useful when you're designing algorithms for non-convex problems. So now and then I've had colleagues ask me, where can I find a proof of this? Where can I find a proof of that? So hopefully some of these references and rough ideas that will outline give you those kinds of references. And I'll talk about non-convex optimization, and then in the very last part, I'll talk a little bit at a more high level about a topic of my current favorite interest that is related to the class of geometric optimization problems. And I'll make clear more precisely what I mean by this heavily overloaded word called geometric. So it could mean many things for different people, but I'll give a very high level motivation about that towards the end. Hopefully you find it interesting. So the slides of the first two lectures are already online on my web page. Holger sent out a link. I will upload this later in a couple of days. And in case anybody has any questions at any point, maybe not now, maybe in the coming weeks, few months down the line, don't be shy, feel free to email me. I usually reply if the question is good. So, okay, so let's, that was what we talked about. So just quickly to remind you, I went through, of course, superficially through many things related to convex analysis and optimization, gradient style methods. I mostly actually talked about only non-smooth optimization and operator splitting methods last time. I left as bonus material for you in the slides, which I did not quite get to cover, stuff on stochastic convex optimization and large-scale convex optimization. And for those of you who work with large-scale data, that's a theme that you have also seen in Francis Bach's talk, and you can look at a short summary of those ideas in my slides. It's online. And today I will talk about, as I said, non-convex mathematical models and algorithms, and one of those will again be reusing some ideas from last time for large-scale non-convex and non-smooth optimization. And no surprises, ultimately we will live in the easier world of gradients, so it'll be some kind of gradient-based thing, no surprises there. And gradient-based ideas extend, one should always keep them in mind. Rather than thinking of gradient as something magical, maybe one of the best ways for an optimization person to think of a gradient beyond vector giving direction of descent, etc., is that by its very definition, in every space where we construct a gradient or something that mimics a gradient, we are by definition constructing a first order local approximation, linearizing some sort of, and that idea will shine through, not directly under the name gradient, but under the idea of building local approximations to aid you in optimization. That will be one of the things I will talk about for non-convex optimization. Okay, just I have 2 or 3 of these annoying lists in the lectures, so hopefully you don't get too annoyed by these lists, but it's just to remind you some of the popular non-convex problems that you have definitely seen, if not all, most of them you may have seen. The most basic non-convex problem, which is morally actually almost convex, is the SVD or PCA, and bunch of other eigenvalue problems, like generalized eigenvalues and so on. I'll talk about one of those. Then other less, and these two are globally solvable. The other ones, most of the other ones are not really globally optimizable, so they're really truly difficult non-convex problems. And more popular things in machine learning community are things like matrix factorization, tensor factorization, and clustering data, constrained matrix factorizations, and topic models. You may have heard of latent Dirichlet allocation or other such topic models where data mining companies try to look at a bunch of millions of documents and automatically group them into topics for your consumption. So that's very heavily used by companies such as Yahoo, Google, etc. And then classical for statistics people are mixture models, hierarchical mixture models, these days deep mixture models coming from deep neural networks. All of these are standard kind of non-convex problems which govern the kinds of methods we are taking interest in. And I'm, of course, absolutely not talking about any of the other really cool non-convex problems that come from discrete and combinatorial optimization, including the ones for which big band of methods related to convex relaxations, tight convex relaxations, semi-definite programming relaxations, etc., is of great interest. Of course, I can't cover everything, but it's good to know that this is a rich world of ideas out there, and they connect with each other in a nice way. And so when I talk about geometric optimization, I really mean optimization either on manifolds, which may be Riemannian or non-Riemannian manifolds, or even more generally, optimization in certain metric spaces, which have a geodesic structure or something like that. And so that's what I really mean by geometric optimization. I'll touch upon it towards the end. And the list goes on. But I'm interested actually in pretty much all the problems in here. I haven't really looked at the mixed integer programming because that's very classically operations research, and I'm not in operations research. But otherwise, I'm interested in all these problems, so I listed them. Okay, so just to remind you, we have seen this kind of thing again and again. So this is a standard nonlinear problem. And the important message is this, that if the cost functions or the cost function and the constraint functions, so the cost is f and the constraints are gi's, m different constraints, if all of these are convex, and it's important to remember that if G is convex, then the inequality should be in that direction. So it depends on how much optimization you do, but it's good to train your muscle memory also to write inequalities in the correct direction, whichever way works for you. I like to write all my problems as minimization problems because frequently the problems are convex optimization problems, and you typically don't maximize convex functions so easily. That's typically NP hard. So I try to just train this mnemonic that it's good to write things as less than equal to, at least if you want to exploit convexity, so that you don't make the mistake. But anyhow, so the crucial thing is that under reasonable conditions, we have access to necessary and sufficient conditions of optimality. And one of those is, of course, simplified version of one of those is the so-called Karush-Kuhn-Tucker conditions, like this one. If there are no constraints, m is equal to 0, f is convex. We have looked at this condition so many times. It's necessary and sufficient for convex functions. For non-convex, this type of condition is, of course, only necessary. And therein lies the problem that for non-convex, these necessary conditions are known and you can easily create them, but there are no known simple conditions that are both necessary and sufficient. And when I say simple, you could write down all sorts of conditions, but they might be tautological and computationally hard to verify. And if it's computationally hard to verify, just because it looks algebraically simple, don't get deceived. It's not simple by my definition. And that really is one of the barriers here. That we cannot expect to even have such conditions. But abstractly speaking, it is the lack of these simple conditions that are both necessary and sufficient. Which is why once you start looking at discovering interesting subclasses of non-convex problems, what you're really chasing in the end is a bunch of easy to verify sufficient conditions that guarantee either local or global optimality. So that's the abstract view of these things. And one of the things which even many textbooks skip annoyingly, and people repeatedly use this vocabulary incorrectly, which annoys me all the time, is that, well, one of the things people almost always skip, that I have a candidate solution, which I say alleged solution, maybe feasible point here, maybe. Is it a local minimum? Typically it's skipped, and for good reason, it will be clear, but the myth that persists amongst people who are not in optimization is that, okay, if it's convex, I have an iterative method which spits out something, it is getting me to a global minimum, and if it's a non-convex problem, I have an iterative method, it spits out something, it gives a local minimum. And the literature, including 1 million statistics paper with slight exaggeration, they say, I'm doing log likelihood maximization, and I get to the local maximum. No, you don't, because typically, at best, we can show necessary condition. That without further work, you cannot just say that this is a local minimum or local maximum. It's most likely just a so-called critical point or stationary point where 0 belongs to the subdifferential or gradient disappearing is being satisfied. And means if you look at one of these online communities like math.stack exchange or math overflow, etc., you'll see repeatedly people making this, committing this error there. To the point that it's kind of almost culturally accepted. Even if you write local minimum, the person who knows it will read it as, okay, stationary point or local minimum, and the person who doesn't know, doesn't bother him or her. But I think it's important to make this distinction, and you'll quickly see why. I'll cite an additional theorem for your entertainment there. So recall, this is a toy example from a very famous paper on hardness of non-convex problems. It's good to see this formally once. So there is a famous problem which you may have heard the name of, the subset sum problem. And in a simplified format, we have a set of n integers. And all we are asking is, does this subset of integers contain a subset that adds up to 0? So these are clearly positive and negative integers, otherwise you could answer that trivially. So is there a subset? And there's a version of this which asks that, okay, maybe there's the smallest such subset, because if there is a subset, it need not be unique. There may be several such subsets that achieve the 0. Well, this problem is one of the classical, well-known NP-hard problems. It's in fact an NP-complete problem, because if I give you such a subset, you can quickly verify whether it sums to 0. So it's actually clearly in NP, but it's hard to compute, so it's NP-hard. In other words, written as just an integer program, feasibility question, is there a solution to this bunch of discrete equations? The Zi is just 0, 1 Boolean variable. So subset sum written as a very simple looking, harmless looking, but not harmless problem. And fanciful non-convex optimization version of that, well, minimize this thing plus this cost subject to, z is no longer integer. I relaxed it, but you can stare at it for a moment and see that something that minimizes it because of the second term had better be just either a 0, 1 z in there. And you can see that if you could solve this problem, you could solve subset sum. So this is a very simple toy yet I think instructive illustration which shows you how incredibly hard non-convex problems are. There are some other more entertaining examples in the paper where I took this from, including like writing Fermat's last equation as a non-convex problem and being able to answer it that way. But those are for mathematical entertainment. So another example which may also look comforting but turns out to be discomforting is this type of question. Suppose A is a symmetric matrix. So it's just a real symmetric matrix. I'll only talk about real valued variables today. I'm asking the question, is x equal to 0 not a local minimum? So there's a not in there, so it takes a little 2 extra seconds to parse that. So I'll let you parse that for a second. That's the question we are asking. Minimize that such that x is non-negative. Of course, clearly if A is an element-wise non-negative matrix, the answer is trivial, right? So this is interesting only in the cases where, or if A is a positive semi-definite, symmetric positive semi-definite matrix, even then it's trivial. So clearly for the complement of the trivial class, this becomes tricky. Actually, this is NP hard to answer. And in general, this is one of the reasons why I make sharp distinction between stationarity and local optimality. Even for unconstrained non-convex problems, testing local minimality or even testing if your objective function is bounded below, that it doesn't recess off to minus infinity, these problems can be NP hard for badly chosen non-convex functions. There's in fact a classical paper by I think Sartaj Sahni from 1979, which, or maybe 78, maybe, which says, non-convex quadratic programming with a matrix A that has a single negative eigenvalue. All the other eigenvalues are positive. So it is almost convex, where you would say that, on D minus 1 dimensions it's convex, only 1 dimension is the bad one. Well, even such non-convex QPs are NP hard to solve. So convexity does give you a lot, but you can see that how quickly things become NP hard. And essentially the same example here, but in convex language is this one. So maybe you have seen, so let's use some convex language. I don't know how many of you have seen this before. There's a convex cone called the copositive cone. So like the non-negative orthent, that's a cone. Set of semi-definite matrices, that's a convex cone, if you remember how we defined a convex cone. Convex cone is just a set K where if X belongs to the set K, all non-negative multiples of X also belong to this set K, and the set is in addition convex. So that's a convex cone. Semi-definite matrices trivially form that cone. These matrices, a symmetric, let's say A is a symmetric n by n matrix, and this cone consists of all those matrices which are non-negative for non-negative vectors. Semi-definite cone wouldn't have that last constraint there. This one has that. So you can verify if two matrices satisfy this, then their convex combination continues to satisfy this, and of course non-negative scaling will trivially continue to satisfy this. So it is a convex cone. But just because it's convex doesn't mean it's easy to work with. So that's a slight, tiny bit of misconception which can happen if you don't work so much with optimization, but it's easy to convince yourself that this can happen. Just because something comes with the label convex doesn't make it easy. So, and the reason is very fundamental. I created a convex set over which I'm trying to optimize. If I cannot efficiently test membership in this set, then I can't really optimize over this set. And that's what it boils down to. So this, as I mentioned on the last slide, this is difficult to test. I'll leave this famous matrix as an example for you. If you like to play with Mathematica or by hand with some algebra, it's a nice exercise to verify that this matrix does lie in that set. So 5 by 5 matrix. This is actually a famous matrix in the world of copositive matrices, but it's a very it's an instructive exercise to try it out. Okay, but not every non-convex quadratic looking thing is bad. There are also some good ones, and those are the ones which are ultimately reduce to some kind of eigenvalue problem. So there's this problem that you should know about if you did not yet know about it. This is called the trust region subproblem. A is a symmetric, real symmetric matrix, not necessarily semi-definite. B is some vector, and we are trying to minimize that subject to the one norm of the two norm of x being less than or equal to 1. So this doesn't have that annoying element-wise constraint on x. It has a more spectral looking constraint because it's a constraint on the entire norm, and the L2 norm is invariant under unitary transformations, which makes it slightly nicer. And pretty much that's what makes this thing more tractable. So this problem is called the trust region subproblem. It's one of the most important building blocks in large scale or small scale nonlinear optimization. It's a subroutine of many solvers, which basically build a quadratic approximation to the nonlinear cost function, and then when minimizing that quadratic approximation, because it's a nonlinear function, the quadratic approximation's Hessian need not be semi-definite. So this type of stuff comes up, and then when optimizing this approximation, you sort of end up minimizing this subproblem where this norm ball gives the so-called trust region. So it's a very famous problem. Solving it, and there are lots of different methods for solving it. One of the most famous one is Morey-Sorensen's Newton method, and it's still used. MATLAB's default solver for fmin-con in MATLAB and fmin unconstrained in MATLAB, they're not really that great solvers, but ultimately they all rely on trust region solvers to do their solving. Anyhow, this problem is it's solvable can actually be showed from exercise 1 in lecture 1, but we'll not see how. Let's just look at the default kind of way. So I try to solve it. I write this Lagrangian. I'm trying to build a dual here, if you remember. So this is I introduced a Lagrange multiplier to deal with the constraint. So this is the Lagrangian. I minimize the Lagrangian over x to obtain the dual cost function, which will be a function of theta. So you minimize it, and what do you notice? Well, if B doesn't belong to the range space of this matrix, then you can pick a suitable x in the null space to drive this thing down to minus infinity. So that dual cost function, and we try to maximize the dual cost function. So if there's a subset on which it goes to minus infinity, that's the infeasible part. So we remove that. So the dual cost function becomes essentially this, subject to this constraint, and B belongs to that range space. Anyhow, so this is, you take that, so the dual optimization problem, I've rewritten it. It's a maximization problem. The details are not so crucial except this part, that now you take an eigen decomposition of A. I'm just trying to simplify this problem as a problem over theta. We have to just find the best theta there, okay? That's what we're trying to do, subject to all these constraints. It takes some effort to implement these constraints and write a solver. I don't expect you to immediately get it. There's like tens of papers written about it, but the key idea is just this. You took the original problem, wrote the Lagrangian, figured out its optimality constraints, rewrote that to figure out a dual problem, and then A is a symmetric matrix, so it's diagonalizable using unitary or orthogonal matrices here. So you diagonalize it and rewrite this thing in this notation after introducing these eigenvectors of A. And this you can see is just a convex, so this is maximization of something concave, which is the same as minimization of something convex, so it's actually a convex optimization problem. Where? Oh yeah, that should be theta I, thanks. So the good thing is, these problems go by the name of problems with hidden convexity. So this was essentially convex, but the convexity was hidden. And there are many such problems where the original formulation doesn't immediately show you that it's convex. And extracting the hidden convexity can sometimes be fairly non-trivial. And this particular problem is very important, and if you remember nothing else, this is one of the things to remember from today. Yes, you can recover solution to the primal. Actually, you don't really solve it this way. You don't actually even need to do eigen decomposition to solve it. This is just to schematically illustrate that it's solvable. To solve it, you actually, the good methods, because it's a single variable optimization problem in the dual, so it turns out to a root finding problem. And to find that root, it's a fairly clever, simple in hindsight, but fairly clever method of Moret-Sorensen that avoids doing eigen decomposition, but just because A plus theta I, we constrained it to be semi-definite, it just plays around with a suitable Cholesky decomposition. So from a complexity theoretic viewpoint, that also is in a different category because you avoided eigen decomposition. So yeah, solving this is a pretty interesting thing. And I'll mention here, I don't have slides on that. People have over the years, including many people in signal processing, considered extensions of this. That what if instead of this isotropic constraint x transpose x less than equal to 1, I had x transpose bx less than equal to 1, where B is another symmetric matrix. Or I had a couple of quadratic constraints, not just one. Do the problems still remain tractable? So there is no clear idea. All of these reduce ultimately to some kind of sums of squares questions. But for a single quadratic with a more general quadratic constraint, that essentially reduces to what you would suspect, some kind of generalized eigenvalue problem, so that is tractable. There are versions under suitable conditions where with even two quadratic constraints we can solve. And these are subproblems which occur in so-called QC-QP, quadratically constrained quadratic programs. Those are kind of the tractable versions. And after that, there's a smattering of different sufficient conditions under which these remain tractable. But mostly, that's kind of the limit. But there's no clear consensus on when these things are solvable as you add more constraints. And but it's certain, if you add lots of constraints, you can easily end up writing these quadratically constrained quadratic programs that are NP hard, because you can reduce max cut into one of these problems with sufficient number of quadratic constraints. So there's a nice, this kind of an open area. Okay, so that's about it for the fundamental non-convex problems that I wanted to mention. There's many more. A colleague of mine and I, we maintain a list of non-convex problems which are kind of tractable and solvable in polytime. Someday I hope to put that list on my web page, because it's over the years you collect nice examples of tractable non-convex problems. Each time you have a new example that expands the class of mathematical models that fall within your grasp to be provably solvable to global optimality. So now let's talk about, after this, a couple of very simple classical matrix non-convex problems. The first one being matrix factorization. And this is, until I talk about geometric optimization, I'm essentially going to be talking about matrix factorization. It's just an example to illustrate the general principles. The general principles apply to certainly beyond matrix factorization problems. So just to remind you, the first matrix factorization that most people look at is either eigenvalue decomposition or singular value decomposition. So of course we know this classical textbook theorem, which probably is to be credited to Schmidt from 1890s at least, the guy whose name comes up with the Hilbert-Schmidt norm, that Schmidt, in Gram-Schmidt, etc. But I just cited a textbook for you here. So this is an optimization result. The SVD is a non-convex problem because we are taking a matrix A, and we'll quickly see exactly through this slide why it is a non-convex problem. You are given input matrix A, and you're trying to find, this is the truncated SVD, a rank K matrix that is nearest to the input matrix in a spectral norm, which means the operator norm, Frobenius norm, or any of the Schatten family of norms, etc., any unitarily invariant norm, essentially. And so it's an optimization problem where we end up having essentially orthogonality constraints on those variables. So it's, and that's the non-convexity. And of course, rank constraint is famous non-convex constraint. This, in the slides, I'm leaving this as an exercise to at least prove the first part. Both are fairly easy proofs, but if you haven't ever seen them in a linear algebra class in your life, it's good to prove these results. There are several ways of proving these results, including the more general claim that I made. If the norm is any unitarily invariant norm, then SVD gives you the best rank K approximation to the input matrix. That follows from classical inequalities in matrix analysis. But the proof for operator norm is pretty much by definition and simple linear algebra. I'm leaving it in the slides for your later entertainment. I'm not going to go through it now. So very straightforward linear algebra proof. Okay. Now, after SVD, SVD is at the heart of principal components analysis, which is still consumed regularly by anybody playing with data, though these days by anybody playing with smaller data, not those playing with bigger data. But still, it's one of the fundamentally important things because people like to view data as living in Euclidean spaces. So, and many years ago, let's say 99, 98, people who were using these factor models like SVD, PCA, etc. Oh, before I go further, a slight digression. There was one time back in the Stone Age of data mining and machine learning, somebody who managed to use SVD to analyze their data could write a paper about that. It's kind of almost ridiculous from today's standpoint, but surprisingly means this technique was limited mostly to people in the world of linear algebra and biometrics and statistics. Not that many people knew about it, surprisingly. It means, of course, now everybody knows about it. And then around that time, people who were analyzing images, text, etc., they said, well, our input data is encoded to be non-negative, and when we try to build a low-rank factorization into U sigma V transpose, etc., those things end up having negative numbers in them. We don't like that. That was definitely the motivation. And then, of course, you build a story around it that you want to visualize it, these are intensities, or you want to interpret it. All of those are very valuable motivations that come from an application. So these types of questions often arise in applications where you actually want to use these techniques. So in one of those applications, then they said, well, we are looking for, essentially we are looking to get a low rank approximation of the data. And the SVD, either it was yielding, even if my input data was sparse, the SVD ends up giving very dense factors. So I wanted to somehow have just sparse factors. If it were non-negative data, and I'm trying to approximate it with, and I wanted to, that's why I keep interpretability to approximate my input data by stuff that is low rank but lives in the same space. So you added a non-negativity constraint in there. And that's what led to non-negative matrix factorization, that you are trying to get a low rank factorization, but unlike the U sigma V transpose where U and V have orthogonality constraints and those optimality properties, we have non-negativity constraints. And the two most popular versions of the non-negative matrix factorization, when we try to get that factorization, somehow you have to quantify the quality of that approximation. And to quantify that, one of the most commonly used is the least squares factorization model, and one is the Kullback-Leibler divergence model. Different communities prefer different ones. In computer graphics, people end up using that more. In some statistics, people end up using that more. This is more widely used. Both of these problems are, of course, NP hard to solve. Formal proof was given though in 2007 by Stephen Pavasis. But recently in theoretical computer science, there has been a pretty interesting development. I'm not going to talk about that, but I'll just tell you that even for this problem, which is NP hard, people continue looking at it and at its extensions to tensors and non-negative tensors, and they try to identify some special properties of the input matrix A, upon exploiting which you can actually solve these NP hard problems to global optimality. So that's a trend sequence of works in the past few years which became quite popular. So, but I'm just pointing out that's why here that exists. I'll just look at only the simplistic methods which do not assume anything about A other than non-negativity. So the trivial so this is kind of a list of methods which illustrates several different ideas. So the first one is really a hack, lazy person's method, let's call it, is I want low rank factorization, I compute SVD, anything that is negative, I make it 0. I shouldn't call it an algorithm, means it's something. I called it a hack, that's why. Then more interesting methods are based on ideas of alternating minimization or on the idea of majorization minimization. I'm going to talk about these. I'm not going to talk about global optimization methods, which would include techniques based on branch and bound and whatnot to actually get to the global optimum, potentially in exponential time, but suppose you're really desperate to solve for the global optimum. And then I'll actually revisit what I didn't really quite talk about in lecture 2, are the large scale methods for this problem. So the generic scheme for this types of problem is we're trying to minimize a cost function of two variables, B and C. So remember the cost function was A minus B times C Frobenius norm square. And this is a generic pseudocode here. You somehow initialize, and I'll pause here to tell you, yeah.
Can you go back one slide, please? 2 slides. You don't regularize the decomposition with respect to, you just ask that they are positive.
It's not unique.
No negative.
Yeah.
It is unique.
It is not. It cannot be.
And so you don't regularize it at all.
In practice, we do.
For instance, by assuming that they are sparse.
You normalize them or put some kind of sparsity penalty. And one of the prime reasons to do that, as you already suspect, there's a product B times C. So if B is a solution, C is a solution, B multiplied with a matrix T and C multiplied by T inverse as long as B times T is non-negative and T inverse times C is non-negative, is also a solution. So there's a vast amount of non-identifiability in there. To decrease that, you regularize.
Okay, then I'm curious to know what happens with alternating minimization.
Yeah, I'm going to talk about that. I'm just going to give high level on that. So here is the generic idea for several such problems. Cost function depends on two variables. I try to iteratively construct a method which does descent. Of course, trying to ensure that this inequality is strict unless ck plus 1 is exactly equal to ck, of course. And you construct these types of methods. Alternating minimization is one of those. For example, this is something which people publish several papers on. It always shocks me, but I guess in hindsight one is always shocked. So there's something called alternating least squares. Once again, take the problem, well, if you fix A and B, it's a good old least squares problem in C, because I ignored the constraints, and then I just truncate. This is a published method, several papers on that, quite annoying. Anyhow, it's a hack which was marketed under these names. They didn't, of course, write that letter, the word but there. And that is that it need not guarantee descent. So it is truly a hack. It is okay to try it as a hack. Nothing wrong with trying a hack to establish a baseline. But to think further, just a toy illustration of why merely truncating is a bad idea. If this is an unconstrained problem, this is a quadratic cost function. Setting the gradient of the quadratic cost function equal to 0 will bring you to the unconstrained minimum here. Truncating it will throw you on that axis, whereas the true unconstrained minimum lies there. So it's really a bad idea. And in high dimensions, this becomes very pronounced. And this alternating least squares is not even guaranteed to converge. I think it can oscillate, at least for the constraint problem. And I've seen that oscillation happen in practice. Anyhow, it's still used by some people. Then you may say, well, what we can do is, rather than alternating least squares, solve alternating non-negative least squares. Well, of course, it is then by construction guaranteed to descent and be a well-defined method. And under some slight additional work, you can show that actually it goes towards, it descends, so it's doing the right thing. And if it's descending enough, it actually goes towards stationary point. Of course, computationally more demanding, because now you're trying to solve a constraint problem at each step. But that's okay. At least it's formally correct. And the convergence kind of follows from this. There are several ways to analyze convergence, but this is a good theorem to know about from Grippo and Chadrone from 2000. Basically, if you have a cost function f of two blocks of variables, x1 and x2, or x comma y, so it's a block separable, so x1 and x2 are this is a Cartesian product, and we assume these are closed convex sets, and assuming that, say, the fixing x1 the problem over x2 has a solution, and fixing x2 problem over x1 has a solution. And a dramatic assumption, which for actual problems takes work to show, that the sequence of that alternating actually has limit points, then every limit point is stationary. So this is called the two-block alternating minimization, or the two-block block coordinate descent. Yeah.
So which kind of assumptions are
on F?
just continuous with direction?
Yeah.
And what happens to you if it is a bit weaker than that? So it is
So if it's
or is convex in both variables but not jointly convex?
Yeah, I think it's there is no general purpose result, I think.
You don't know. Okay.
If it is, yeah, I think because
Would be good to have the same theorem somehow, assuming that f is convex in each individual variable, not being convex in both, and having the same theorem.
so the result that is there is more from the generalized block coordinate descent theory from Paul Tseng and Tom Luo, which says that the non-smooth part, if that is separable, so if the non-smooth part separates out, then coordinate descent cannot get stuck at a corner. Otherwise, even with this biconvex structure that you're assuming, you could get stuck at a corner by doing coordinate descent for certain problems, not for all problems. So in general, I think there may not be exactly this theorem, but under some, actually not exactly BCD, but a slightly different method will do the job. So I'm going to comment on that theorem also very quickly. So I just wanted to mention this alternating minimization theorem. It's a special case of doing coordinate descent with two blocks. Textbook results, as you may find in Dmitry Bertsekas' textbook, assume that the subproblems have unique solutions. But in the two-block case, the subproblems need not have unique solutions. But that uniqueness is traded off by writing such a thing, sequences, limit points. But it's, so for two-block case, essentially you can remember, for two-block case, one can make a more general convergence theorem. If there are more than two blocks, then theory of coordinate descent is less complete. Same thing that happened with Douglas, Rachford, ADMM, etc. Going from two blocks to multiple blocks, things get trickier. Okay, so this one is some slightly related to answer Massimo's question. I'll just mention. Slight generalization of alternating minimization or BCD is still again block coordinate descent, is this type of structure that you have a function which is differentiable. The joint one is differentiable, the individual ones need not. So it's still not really fully the setup that you wanted. So one toy example would be where this is like x minus y. That's why I'm calling it alternating proximal method. And you could run this type of iteration. So you alternatingly minimize over x and y. So this is again alternating minimization. But for this, there is a more refined convergence theory. So this is clickable link from my slides by Atush et al. On proximal alternating methods. These are non-convex problems. And there is follow-up work to this which gives under other conditions and assumptions on cost functions more refined results. But this one is also good to know. One thing, one caveat that I'll mention to you, which all of these papers ignore, they could probably capture that, but they just ignore that. When the convergence theory here, the way it is written in the papers, it assumes that xk plus 1 is in the argmin, which means you're able to solve this globally. But as we know, this is a continuous optimization problem. At best, we are going to be able to solve it to epsilon accuracy, not exactly. That means the subroutine gives back an inexact result. If the amount of inexactness is not too large, then most likely the rest of the convergence theory will go through with this extra perturbation coming from inexactness. But if the subproblem happens to not get solved very accurately and the errors accumulate, maybe the overall convergence proof breaks down. That is tacitly ignored in these papers, but one shouldn't ignore that, because the reality of any such alternating problem is you're never going to be solving subproblems exactly. That is partially addressed in one more result that I'll mention, not making it explicit. It's a special case of descent techniques, like the broader family of descent techniques, which gives you some handle on this. Yeah.
Sorry, you remember maybe the result of Bush and the others about their convergence. So do they converge to stationary points or?
They, if I remember, they may even have a local rate of convergence analysis for you. ultimately building upon von Neumann's original alternating projection style arguments as motivation. I'm not covering, but there is additional work for non-convex alternating minimization by Adrian Lewis and co-authors, which also gives local rates of convergence analysis. So typically for non-convex problems, we are happy the moment we can actually prove either descent and then that we converge to a stationary point. If you manage to show a local rate of convergence, that's quite impressive. And of course, if you manage to show a global rate of convergence, that's even more impressive. For convex problems, all these tasks are much easier. But anyhow, so there's a general family. For non-convex problems, people often prefer to have descent techniques. That's kind of the best we can guarantee because of lack of sufficient conditions. And the only difference between large-scale problems and not so large-scale problems, the prime difference is one of them guarantees descent at every step, and the large-scale version guarantees descent in expectation only. And that prime difference allows you to do scalability, but the underlying theme governing this is trying to get descent. So I'll just mention this great class of mathematical techniques that you should definitely know about. If you don't, is that of majorization, minimization for building a descent method. Let's use as example the previous quadratic. And this is a very important class. It's just rewriting actually what we already knew, including gradient descent itself is a majorization, minorization, minimization method. The idea being you have a cost function you want to minimize. It looks difficult to minimize. You build an upper bound, you minimize the upper bound. So these are also called bound optimization methods. Then you build another upper bound and you minimize that, and so on. Or if you're trying to maximize, you build a lower bound, you maximize the lower bound, etc. So this is general idea. Here's a special instantiation of this idea, which gives you a technique. So suppose we were trying to optimize that, and we see that it is convex separately in B and C. So I'll just use f of c to denote the function restricted to C. Here f of c is separable, because Frobenius norm is separable. So it's okay if I'll just illustrate you the idea for a single column of matrix C. And all we are trying to do is construct the update so that we have descent, hopefully strict descent. That's what we are trying to do. I'm not trying to solve the full minimization actually, I'm just trying to ensure a descent. And how do we do descent? This is a generic idea that you have f. So we started out trying to minimize, but actually I should replace that minimization by we are trying to just descend on that. So we construct a function, another function that agrees with f at all when both arguments are equal. Otherwise, it's always an upper bound. So some people call this an auxiliary function. I didn't draw pictures, but you can draw that easily. I mean, it's basically it's, you know, if you had like difficult function, you build, okay, this is I made a lower bound, but at each point you build a nice convex upper bound, then you optimize that, then you again build a nice convex upper bound at that point, and you keep optimizing those bounds. It's a very widely used technique. Everybody in statistics uses it. And then, this is the creative part, you build an upper bound that is easy to optimize. There's an infinite number of choices for building these upper bounds. The creative part is for a given problem, coming up with an upper bound that is easy to minimize. And in fact, it's a constraint problem here, so it better be easy to minimize as a constraint problem. Well, and then you have descent. Why? Here is the proof, very dramatic proof. F at c of t plus 1 should be smaller than f of c of t. This one is by definition. This one is because Ct plus 1 is an argmin. And this one is again by definition. So this technique gives you a way to do descent. Okay. And let's see explicit example of this technique in action for our quadratic problem. And all I'll exploit is convexity of the x square function. So this is convexity, right? If h is a convex function, that's the definition of convexity. So this is our quadratic cost function written out over all the individual elements. Expand it. This is a linear term. I'm not going to bother with it. The quadratic part, again, expanded out in element-wise notation. Now, multiply and divide by those coefficients lambdas. Use convexity. This is your upper bound G. This is how I define G. So this is a generic way to exploit, if there is convexity of individual variables, to exploit convexity to build a bound. Now, okay, we had that, we built this bound. What remains is to pick these lambdas cleverly. They have to be just non-negative and have to add up to 1 so that g of c is equal to f of c. So you pick them in various ways, and we pick them just like that. This you can come up with this term by trying to satisfy that g of c is equal to f of c. So when you try to satisfy that constraint, you may end up constructing that. And with that, this is an exercise. If you use that and you solve the corresponding equation by ignoring the constraint, it turns out that that has a non-negative solution by construction, so you can ignore the constraint. And that yields the so-called famous multiplicative updates algorithm of Lee and Sung, the guys who proposed non-negative matrix factorization, using a very classical technique which has been around since at least 50s under different names. When it was introduced, people didn't widely know it, but I think they had a clever idea to use this technique. And so this is a special example of a vast family of methods which are called methods. We exploited convexity of x square, the famous expectation maximization algorithm from statistics that people have been using since 70s and earlier, that just exploits convexity of minus log x. It is introduced under various names, hidden variables and whatnot, to complicate matters and make things look more impressive, in my opinion, but ultimately it's just minus log x and Jensen's inequality. And that's the beauty of thinking in terms of using convexity as your friend when generating bounds and inequalities. And so our technique is one variant of vast class of methods. And I said pretty much many things, almost any iterative method can be viewed as an method, including gradient descent, where we use the Lipschitz lemma to build a quadratic upper bound, then we minimize the upper bound. So we have already been doing methods. It's kind of tautological. Here, this is the way our function looked like. A class of not necessarily methods, but a class of problems for which people typically use methods is this class called difference of convex functions. So many functions can be written as difference of two convex functions. And when you're trying to minimize, it becomes fx minus gx. Then you apply the idea to g of x. And f of x is already convex. And that leads to a sub-area called DC programming, difference of convex programming. It's always a good idea to try out looking at your non-convex cost function as a difference of convex functions and seeing if this bound optimization idea applies to you. It works sometimes remarkably well in my experience. Okay, but I could go on talking about those, but I'll kind of wrap up and wrap up by mentioning one another generic idea for creating descent methods. This one partially answers what Massimo mentioned. So there is, for the class of non-smooth, non-convex functions, which satisfy some additional growth properties around a stationary point, which you may have seen coming from differential geometry type conditions. You can study a general purpose class of descent methods which at each step guarantee a sufficient amount of decrease. So this term, when you go from xk to xk plus 1, this shows that this is at least the amount of decrease you're having. And then there's another, the second condition is trying to say that, approximately you did an optimal thing, because wk plus 1, the value of a gradient at the next step, that had better be small, roughly speaking, which means you're approximately optimal. So if you have a method which can satisfy this, these are studied to terrible detail in this paper by Atush, Bolte, and Sweter on convergence of generic descent methods, which satisfy the growth condition which comes from, okay, they removed it from the title. It's like, I think the Kurdia-Loyasiewicz condition on growth of gradients around a stationary point. And they provide a framework for analyzing optimization of non-smooth, non-convex functions as long as your method satisfies such properties. So they end up also giving a convergence analysis of, for example, proximal gradient method, but where everything is non-convex, or projected gradient where the set onto which you're projecting is non-convex. And it's interesting because for these types of problems, for non-convex functions, the proximity operator that I talked about last time is not a single valued map. But the theory kind of handles that. Of course, what I don't like about this as a large scale person is I cannot afford to ensure descent at each step. So for me, this thing stops being interesting at that point, unless I can wrap an expectation operator around that, which I can, but I haven't yet written out the details. So there's a bunch of other non-convex methods. I just put this slide because yesterday somebody had asked me about some pointers to other non-convex methods like non-convex ADMM, non-convex Douglas-Rachford, or if you are interested in learning more about alternating minimization for non-convex problems, but guaranteeing global optimality. So that's a line of popular work in recent years, which also extends to some tensor stuff. So there are many such methods. So I think I will just quickly show you then just a toy example of large scale method. Yeah.
With low rank matrix completion using alternating minimization.
Yeah.
You know this paper?
I read it a few years ago, so roughly.
So what is about the content exactly?
So the crux of all these papers that use alternating minimization to solve these non-convex problems. So this is either low rank recovery or matrix completion or denoising. The crux of these is they show under your restricted isometry style assumptions on measurements that if you initialize using SVD, you already come quite close to the global optimum. After that, alternating minimization doesn't screw up. Roughly speaking, that's the content.
Minimization over the singular vectors.
No, so you want to get low rank factorization, you write A is equal approximately B times C. You initialize B using the singular vectors of A originally, but then you just solve this alternating least squares style problem. And the reason they want to do that is so that they don't have to do an SVD at each iteration. So that was roughly the motivation. And that this idea, which roughly saying alternating minimization proves to be more scalable than SVD at each iteration. And these guys were, I think, the first to show that under these some additional assumptions, alternating minimization actually can get you a globally optimal solution to this non-convex problem. Of course, the caveat is you have to initialize it using SVD. So that's an expensive step already. And there's a family of such results out there now by these people and a bunch of other people, which look at some non-convex problems with essentially quadratic cost functions, and for cost functions that are essentially quadratic, pretty much SVD nails it, and they just build on that. But means this is the rough structure of what is done.
With initialization of the learning algorithms for neural networks?
Not so sure. Not so sure.
Because in those problems you do a sort of unsupervised learning, which could be something to do with a sort of PCA.
Mm-hmm.
And then you use some gradients and method to learn the network. And sounds to me kind of related.
There, yeah, it may be tricky in the sense that you may look at probably a simplified version of neural networks where each layer gives a linear map rather than nonlinear map, and then you may maybe mimic some analysis like that by thinking of neural network stuff more in terms of tensor factorization and then using similar ideas. So that certainly seems plausible. Partial work along that line I think exists, but for the general case where there's a nonlinear mapping, I don't know. But it's yeah, it's a good observation. Okay, so it seems like as usual I don't go as fast as I want to, but I really want to show you this large scale simple idea, very simple idea, programmable in 5 lines of MATLAB. As usual, I don't like to have anything that is not programmable in 5 lines of MATLAB. Of course, where each line calls a subroutine which takes 1,000 lines, but we don't speak about that. So large scale methods. So this is mostly stuff in slides of lecture 2 in greater detail. And the idea is that we are trying to minimize a cost function, capital F, and we don't have access to a subroutine that computes the full gradient of F, but only a vector which in expectation is a gradient or subgradient of F. And this is a result of Butsekas from 1970, I guess real analysis result, that if the functions are, maybe I didn't somehow write that here, what we are trying to minimize here is really minimize capital F of x is equal to the minimize the expected value of little f of x comma, or there I. So just that, maybe it's easier to see when I bring it down here. We're just trying to minimize this expected value. That's the stochastic optimization problem. And to compute a subgradient of f, it suffices to take expectation of subgradients of individual guys. That's where the scalability lies. So when we do that method, you can pull out your friend the subgradient method, and instead of using a real subgradient, put in an estimate, which is a subgradient only in expectation, plug and play, or maybe plug and pray, because until you prove it, whether it works or not. But you can show under reasonable, the analysis of this actually is pretty much exactly the same analysis as I showed for the subgradient method. Just happily plug the E operator for expectation around everything, and at one point you will see, okay, I have to also assume that the subgradients that I generate are IID. That makes life simpler. And then the rest of the thing just works out. So this is very frequently used for convex optimization. I am trying to use a similar thing where, okay, now I don't really have the expectation, but I just have a sum of n different functions. And at each step, rather than compute full gradient of f, I just want to compute a gradient of one of the components. So I start somehow, generate uniformly at random an index, and use that incremental gradient. So this can be viewed as stochastic gradient, of course, with probability supported on the discrete set of n items. And these methods can be viewed as running gradient descent, but with an error in the gradient. And stochastic gradient methods, they use an error which is unbiased, so that in expectation the error is 0. You can also have, I'm going to show that quickly, stochastic or incremental methods where the error doesn't go to 0. So more generally, these methods are special cases of the broader idea of using inexact computation to your advantage. Rather than use an exact gradient, I use a stochastic estimate with some control on the error. And that idea is actually very powerful, because the error may come because you're doing distributed computation and some cluster node died, gives some error. You're doing parallel computation asynchronously, things write each other's stuff over, gives some error. If you have some control on this error, all these different flavors of large scale can be analyzed with the same high level view. So I actually wanted to show you why I got into this. I hope my video plays. This is from a toy project of mine from many years ago. We were trying to look at image sequences. This is taken through hot air. So we were looking at images of some underlying object. These are noisy and blurred, both. This is Copernicus crater on the moon. And in bunch of different areas, we have these noisy blurred images, several of those in medical imaging, etc. And this is MRI of a mouse thorax. So it moves a lot, which was probably so these types of problems. So my colleagues were trying to solve these problems, and so what we did was take this problem, write it down as matrix factorization once again, the following way. So this is a slightly simpler problem than general blind deconvolution problem. I'm observing several different y's, each blurred with a different blur operator, but there's the same underlying true image, which I'm assuming. So I really have access to a lot of data about the same X. And I don't really care if I do such a great job on estimating the blur kernels, because this is a moving video, but I want to do a good job on X. And there's potentially different noise in there. I may or may not have some assumptions. So this was exactly our setup. And we can write it in a matrix factorization format that I have all these video frames as image frames as columns. This is approximated by these blur operators operating on the underlying guy. And of course, if you write the convolution in linear operator notation, you can write it as matrix vector. And so I just wrote this as, okay, y is x times a. So this is really just the multi-frame denoising or plus deconvolution problem. I actually call it deblurring because we don't always assume a convolution operator. Matrix factorization problem. And so suppose I had 5,000 frames of that size. Of course, if you don't exploit that A as a convolution by brute force too many parameters, even if you exploit that it's a convolution, it still is a large number of parameters. And even if you, so alternating minimization was impractical for us. So of course, what remains to do is then, when in doubt, do the simplest thing, is rewrite this problem. Yeah.
I have a funny question. Yeah. Impractical means that you even didn't try, or you tried and said, okay, after 5 iterations is enough, not to try more.
So we tried, but you can't even sometimes run 1 iteration, not even 5. So, so what we do is, okay, we say what we want is, we wrote a very simple mathematical model ignoring, to the annoyance of some people, lots of physics that goes into constructing these point spread functions and whatnot, and many things. This is like the big data way of thinking, maybe, that I'll just let my data dictate what happens. So we wrote a simple mathematical model. We had some regularization. Okay, we want an image X and some regularization on the blur operator. And the answer is now pretty simple. I wrote it for you in this specific notation for a reason. I observe an image. I use my current guess of the deblurred image to estimate the blur operator, and then I solve a convex optimization subproblem to update my guess of the true image. So of course, modeling the blur kernel can be a separate talk in itself, because we worked with spatially varying blur kernels, so doing that efficiently so that you can do the short-time Fourier transform, etc., that takes effort. And the convex subproblems, they are actually constrained convex optimization subproblems. Solving them properly takes time, and then we are doing all these steps further inexactly, because what we wanted was, we built a telescope, attached a camera to that, recorded the incoming data, and you run the computation on a GPU so that the real-time deblurred output for you is right there. So there's other things in there. Yeah.
Sorry,
Yeah. So anyhow, so the interesting thing is, how do we analyze this? So first we built it. So first we built it, implemented it, it worked well. But the annoying thing was, how do you analyze this procedure? And the key idea there is just, this is what we actually did. So this is formalization of what we did. So you're minimizing cost function of two variables. You write it like that. Write the inner term as f of x, and now it's an optimization problem over x. F is a non-convex function now of x.
Okay, this is sort of stochastic.
Yeah. And then I write it in my favorite format, cost function plus regularizer. So if you essentially eliminate a by minimizing it out, you get f of x. But now f is non-convex. This is a regularized non-convex problem. I am not going to truly optimize over a, because that would mean optimizing over 5,000 different a's. And that's where this incremental / stochastic idea proves useful. That f, I never truly compute f, I just use estimates of f. That's how you get scalability. So remember our friend proximal gradient iteration? Well, the idea to scalability was the gradient is computed with some error, and maybe even the prox operator is computed with some error, doesn't matter. And using that, so the iteration that I showed you, take an image, update the blur, then update the image, that is exactly an instance of this, where instead of using full f of x, we just use one of the little f's, which means corresponding to one image or to a batch of 10 images. And to get that single stochastic gradient, you need to solve a convex optimization subproblem, which of course you will not be able to solve exactly with some error, but that's putting together the convex things that we learned and the stochastic optimization that we learned to solve a challenging non-convex problem by building on it. And then there's some kind of theorem which was at that point satisfactory to me, that this procedure, the limit points, if it generates any, they're all approximately stationary. Approximately stationary because I'm doing computation with error, and the error is not going away to 0 in the limit k goes to infinity. So you will not really be able to say something more than approximate stationarity. But at least you're doing the right thing. And then more recently, with some better assumptions on, say, the error going away to 0 and whatnot, quite exciting result that I wanted to tell you, not mine, it's by Said Gadimi and Guangai Lan on one of the few global non-asymptotic rates of convergence for non-convex scalable optimization. That you actually run this method which we are running, but this is purely differentiable optimization. Then, because this is non-convex optimization, it's too much to ask for being able to bound f minus f star, where f star is the global optimum. So what you do instead is you just measure how rapidly do you satisfy a necessary condition. This is an unconstrained problem, so norm of the gradient going to 0 is a necessary condition. So you try to see how fast do you become stationary. And that itself, this is a recent result, so it's published in 2013. The proof is extremely simple. That's the nice thing about it. That essentially like the subgradient method, after to get to an epsilon accurate solution, which means to get to a solution where in expectation the norm of the gradient square is less than or equal to epsilon. So to get to an epsilon accurate solution, you need O of 1 by epsilon square steps. So this is analysis of essentially stochastic gradient methods, non-asymptotic convergence for non-convex problems. It's quite impressive. So, and there has been follow-up on this. There's a bunch of follow-up that I listed. People working on incremental majorization, minimization with at most convergence to stationarity. Incremental, distributed, etc. put everything together, but ultimately, hinging on the idea that you can control the errors. So that's why these keywords shouldn't disturb you. For ADMM, these two don't just can go to stationary points, and then a parallelized version of the previous slide is in this recent paper from 20. So it's a very active area to understand large-scale non-convex methods better. It's an active area of research. And I think, unfortunately, I took up too much time. I didn't yet get to tell you about this, but I think it's kind of bad, but I don't want to take you through an entire new idea right now. I don't have the time for that. But even if I don't take you through that idea, I'll just mention then two things before beginning to wrap up. One is that so far we optimized in vector spaces. This was anyways meant to be high level. So this is my favorite topic, so I have to tell you a little bit about that. But there are several problems that we look at where the variables that we are interested in optimizing need not come from just vector space. They may come from manifolds like hypersphere, orthogonal matrices, or some other complicated surfaces. We assume that we know the manifold on which we are optimizing. Or, of course, even when doing convex optimization, your convex sets may have additional structure, like you're working on the probability simplex, or you're working with some very remarkably structured polyhedra, or you're working on our friend the semi-definite cone. These are not arbitrary convex sets, they are sets with remarkable structure, which carries more structure than just the Euclidean structure. And these ideas go further to optimizing in metric spaces. So one of the cool metric spaces is the space of phylogenetic trees, or space of trees. It's a discrete combinatorial set, but this forms a metric space called the tree space, which is a space of non-positive curvature. So you can actually do convex optimization on that space. It's a pretty cool space to know about. And things that are popular maybe in probability and graphics, like working in spaces of probability measures, making them spaces using Wasserstein metric, doing optimal transport, etc. There's a bunch of things which are different forms in which geometry occurs. And the one that I had just wanted to mention was, let's unfortunately skip all these nice slides, but the class, the geometric optimization that I want you to know about is just this very simple viewpoint that Euclidean convexity, or rather vector space convexity, is just convexity along a straight line. You have x and y, join them by the shortest path. In linear space, this is a straight line in Euclidean space. And then the function at the endpoints is smaller than its interpolated value. The function in the middle is smaller than its interpolated value at the endpoints. If you happen to be in a space which is not a linear space but a curved space, then function satisfying similar inequality of convexity along the curve. This just curved convexity, which is called geodesic convexity. And it has been studied and developed in great detail by some of these famous mathematicians, Alexandrov, then Busemann, Cartan, this book by Britson and Hefflinger. And these metric spaces were given the name cat-zero space by Misha Gromov. And some of the fundamental results for these were also derived back in the day by Grisha Perelman, who worked on, of course, everybody knows what he worked on. But these are pretty cool spaces to do optimization on. And the one final thing that I wanted to mention for these spaces is the set of positive definite matrices, one of my favorite sets. It's not only a Euclidean convex cone, it also forms this type of manifold in which you can define convexity along curves. And on this manifold, the curve, which is also in other words known as geodesic between x and y, has a nice closed form formula. And functions that along that curve satisfy convexity, they're called geodesically convex functions. And it's a pretty cool convexity to know about, because like log determinant function, which is minus log det, is one of the most famous convex functions. It's used as the barrier function in convex optimization, and it's used in the normalization constant of Gaussians, etc. That function, so log of det of x is concave in the Euclidean sense, but it is concave in the manifold sense. That's pretty remarkable. Matrix permanents, which just a byproduct of this result, matrix permanents do not enjoy any such convexity property in Euclidean space, but on the manifold they end up being convex. I don't know what to do with that, but it's a cute little result, and many things like that. But unfortunately, I'm out of time. I won't be able to show you some of the really cool things you can do with this convexity. So that's, I'm sorry about that. But what I will conclude by saying is that I maintain a web page. This is clickable, which contains oncoming results with this curved notion of convexity, eventually growing beyond the positive definite space. And I'll just say that, of course, there were hundreds of things I didn't talk about. And these are topics which are all related to many things I've just touched upon. And I'll put that list in there for the interested people to see that what I covered in these slides, of course, is a very tiny fraction of the interesting things that are connected with whatever I spoke. So I think with that, I will stop. Thanks.
Yeah, thanks very much for these very nice lectures. Other questions?
Yeah.
Two questions. First is, could you go back to the slide before the page?
With?
And then the other question is there something that's like, I mean, I know you kind of flew through the geometric optimizations, but is there something like the subdifferential for non-singular points on a variety?
I think for I don't really know if I fully understand all the words in your question, but I think for many of the manifolds, one can define notions of subdifferentials if you have a corresponding notion of geodesics, because subdifferential from ordinary convexity gives you the first order approximation, and moving along a tiny bit along a geodesic also gives you first order approximation. If things are differentiable, then there is essentially locally a unique way to move along. If things are not differentiable, locally there is not a unique way to move along, but there may still be a way to move along. And using that, one can extend the notion of subdifferentials to several manifolds, but I don't know the full story. So most likely there is a book on geodesic flows by Ambrosio and Giglio. These are, I think, I don't remember if there's another author. There's a very famous book on this. Yeah, Savare. So these guys have a very, it's a little monograph on geodesic flows in metric spaces, and then there's a textbook on metric geometry by I think Sergei Ivanov, or maybe not Sergei Ivanov. Sorry, it's by Burago, B-U-R-A-G-O. They have a textbook on metric geometry which may develop some of these things, including local metric differentiability properties. So means you are probably just in the case of a smooth manifold, or maybe not smooth, but at least on a manifold. But even these ideas go beyond just manifolds. So most likely there's stuff out there. I'm just beginning to look at non-smooth optimization on these spaces, so I don't have complete idea yet.
Maybe a stupid question, but from the physics point of view. So very often finding, say, ground states of physical systems simply amounts to smallest eigenvalue problems of a Hamiltonian matrix, which in many systems may be still finite dimensional, yet massive in size. And there are some interesting recent results as to asking whether the lowest eigenvalue is gapped, in the sense that there's a finite difference to the second largest, or second smallest eigenvalue. And some of these questions are in certain contexts decidable, and in other cases they're even non-decidable in the Turing sense of being equivalent to the halting problem. Have you encountered any of those types of questions which might even be undecidable when you ask about the topology of certain minima you are after in the optimization techniques?
I haven't encountered, but I've seen, for example, like word problems on groups which are undecidable, which are of a similar solve an equation format, where many of these things that are undecidable are sometimes undecidable on only a very small pathological set, but are actually decidable in expectation, roughly speaking. So there is this general, I had recently read an article, a summary of an article by some people who work in set theory, who analyzed these types of questions, not for the Hamiltonian case from physics, but for giving explicit examples where of couple of problems which are generally undecidable, but under a slightly modified model, in expectation or in other formalisms, actually decidable. But I can try to dig up what I have in mind, because I just have the picture of that, and
I might ask you for a reference.
yeah. Because the other thing, the only thing related to this physics type question that I have encountered is detecting if a state is entangled or not, but which is a convex set, but membership testing is hard.
Yeah, it's NP hard.
Yeah.
And so related to that is, in the literature which you covered, where sometimes problems are classified as NP hard, are you sure it's really NP hard and not at
okay. So that's a good one. I have to double check if it's just NP hard or worse, because it can easily happen that it's worse, but maybe it's not undecidable, but maybe, okay, it's NP hard, but it is very strongly NP hard in the sense that even getting an approximate solution to that may be NP hard. But if it goes to undecidability because it involves solving some system of non-commutative equations or something, then I don't know. So, okay, but need to double check that. That's pretty. Yeah, I don't exactly remember the status of that. Sorry. Well, otherwise, thanks for listening. Feel free to catch me during the coffee break, because like I typically always drink the coffee here. And like I said, if you at any point have any questions, comments, suggestions regarding this stuff that I talked about, not necessarily on my slides, feel free